let's see here. So I've said pretty much all I have to say about collision. So I mean, I'll entertain questions about that once we have a free day or two to talk about the WebAssign later. But at the moment, I'm going to go on to the topic of rotational motion. So here we go. So to start with, I will resist the urge to talk about the three-dimensional aspect of it, and I'll just talk about it in sort of a one-dimensional sense. So pretty much what we're interested in here is something along the lines of you've got some motion along the arc of some circle or something, right? And so you have some center point, and you have some radius, right? Right. So there's some radius that you're going along, and right. And you can talk about the arc length, which is subtended. And so let's see here. And so if the arc length is subtended, you can talk about the theta in radians, of course. Now, how does the arc length subtended and the angle in radians relate to the radius? What's the fundamental relation here? How are they? What's that? S is equal to what?
Theta r.
Yeah, S is equal to r theta. Sorry, theta r would be incorrect. No, I'm just kidding. No, you go either way. These numbers, they commute, right? So in particular, you know, when I was a student, it always, for some reason, comforting to me, I would think in my brain, where else would I think? I don't know. But, you know, okay, so like, hey, check it out. Theta equals to 2 pi gives me S is equal to r times 2 pi. Hey, there's a good reason to write theta r, because then I would have already written 2 pi r, which for some reason is psychologically comforting. Because that, of course, is the circumference of a circle, right? So the circumference of a circle is 2 pi r, and that is only true. I mean, S is equal to r theta only if we use theta in radians, right? Of course, you can also convert to degrees. How do you convert from degrees to radians?
Multiplied by 180 over time.
Yeah. Converting to degrees is a very simple relation. 360 degrees is equal to 2 pi radians. In some sense, both this word radians and this symbol degrees, I mean, this is just a nomenclature system of notation to indicate that that's how you're measuring the angle. Neither of those are really genuine units, right? Those, I mean, if you look at the formula for theta, theta is equal to S over r, right? So it's dimensionless, because it's the ratio of two lengths. And something similar is true for degrees. But this is the, you know, this is the way to convert. So for example, if I have, say, pi radians, I can multiply by, and of course nobody wants to use 2 pi and 360 when you could also use what? 180 degrees is equal to pi radians. Oh, it looks like that's not a very exciting conversion. So let's see here. How about, there we go, 0.2. 0.2 pi radians is what? So you multiply by 180 degrees, you divide by pi radians, the radians cancel, and you're left with what? Oh, the pi's cancel. 0.2 times 180, 36 degrees. So. Now 0.2 times pi is actually about what? Pi is 3.14, right? So 0.2 times 3.14 is what? What is it?
0.628.
0.628, yeah. So 0.628 radians is 36 degrees. So what's 1 radian? Multiply by 180 degrees, divide by pi radians, what do you got? In other words, what's 180 divided by 3.14? 159 double? 57.4 degrees. I think something like that. Okay, so anyway, that's how you can convert, right? So that's about all I have to say about that. But on occasion, you'll also talk, what's the other thing people like to play with? Revolutions, right? How many revolutions are there? How do revolutions figure into the story?
One revolution is 2 pi.
Yeah, 1 revolution is equal to 360 degrees, is equal to 2 pi radians. So you can also play games with revolutions. Okay? All right, so let me get back to the interesting part. I'm going to erase all this. Before I erase it, though, is it safe to erase it?
I think so.
Okay.
But can you just don't use the green color?
I like the green color though sometimes.
Let me zoom in a little bit.
You can zoom in. Oh, you have to actually. Yeah,
It's good. They can pose and.
Excuse me. All right. So once you know that arc length is equal to s is equal to r theta, then what do we always do in here? Like once we have some sort of fundamental relation. For example, we had center of mass. What do I do next? I differentiated it. I found relations about the velocity of the center of mass as it relates to the velocity of the constituent particles. And I differentiated again. I found things about the acceleration of the center of mass relative to the constituent particles' accelerations. I'm going to play the same game here. Differentiate. What do we get? ds dt. What would ds dt mean?
Velocity.
Yeah, it's specifically the speed, right? I'm assuming that the motion's along a circle, right? I assume circular motion. I should say that at the start, probably. If the motion is not strictly circular, I can't just parameterize the motion by just an angle. I need also to have the radius varying. Okay, and that's, well, it's calculus 3, but here I'm assuming circular motion, okay? So, because of that, this isn't, you're right, I mean, that is actually the magnitude of velocity, this is the speed. R is a constant, right, so I have r d theta dt. Now d theta dt is so important that it has a name. I mean, one of its names is theta dot, a notation which I love. But you can also say this, the STP is the so-called tangential velocity, or just v for short. It's the linear speed, right? The tangential speed. And that's equal to r times theta dot. But theta dot, by the way, we call omega. So here, theta dot, or d theta dt, defined to be omega, which is the so-called angular velocity. Okay. What are the units for angular velocity? Well, it's d theta dt, right? So it's radians per second. Of course, I'm talking about the instantaneous angular velocity. And you could also talk about average angular velocities. What would the average angular velocity be if you're so inclined? What would the average be? You just use change in theta over change in t, right? Where that's a finite increment of time. So theta 2 minus theta 1 over t2 minus t1, that's how you calculate the average angular velocity, just like we calculated the average velocity before. Not being content to stop with velocity, what will we do next?
Differentiate again.
Yeah, differentiate. One more time. So then we have d squared s dt squared, which of course would be dv dt, and that would be equal to r times d squared theta dt squared. Now, this right here is the so-called tangential acceleration, and that's equal to r times alpha, where alpha is defined to be d squared theta dt squared, or if you prefer, it's d omega dt. Anyway, however you want to look at it, this guy is the so-called angular acceleration, right? Angular acceleration. So to recap, to get the speed, we take r times the angular velocity. To get the acceleration, tangential acceleration, we do what? We take the angular acceleration times the radius. What other acceleration is at play here? I mean, it's going in a circle, so there's more than just a tangential acceleration. Right. Circular motion, remember earlier in the course we proved that the centripetal acceleration has to be equal to what? V squared over And that's, I would say, that's assumed to be center seeking, right? If you wanted to say the radial direction, if you like that, radial, the radial acceleration would be minus v squared over r, right? So if I was to draw a picture, right, adding to my original picture in green, rebel, the centripetal acceleration would be like this, right? And if you have a tangential acceleration which is increasing in this counterclockwise direction, right? Then that would be like this. R alpha. The total acceleration is the vector sum of these two guys, right? So the total acceleration would be something like this in my picture. That would actually be A, right? And the acceleration is, it's equal to, you know, minus v squared over r, let's say r hat, plus r alpha t hat, where r hat where r hat is the radial vector outward from the center of the motion, and the t hat is the unit tangent vector in the direction. It's a vector in the direction of the velocity. Okay. Okay, so while we're on this, can you think of how would we restate the radial acceleration in terms of, say, these newfound angular terms we have, like angular velocity? Like how would you rephrase the radial acceleration or the centripetal acceleration? I think the centripetal really just is center seeking. Okay, so centripetal is, there's no minus there because centripetal means center seeking, so it's plus v squared over r in the direction of center. How would you rewrite the the radial or centripetal acceleration? Let's say centripetal acceleration AC is equal to v squared over r. How can I rewrite that in terms of this here? I'm sorry?
R omega squared.
R omega squared. Let's see here. So you're like, so that's r omega quantity squared divided by r. So I think I agree with you. That's r squared omega squared divided by r. So lo and behold, we get an r omega squared just as you planned. So there you go. There's a new formula. The centripetal acceleration we can also write as the radius times the angular velocity squared. Okay? Okay, so let me get to it then. So the first thing we talked about in the case of linear motion was what? We talked about kinematics, right? In other words, I just told you that the acceleration was given, and then we worked out possible motions. We can do the same thing here. So I guess the starting point I would think about would be, how about constant angular acceleration, right? Suppose that the angular acceleration is constant, so consider alpha equals to, let's say, alpha naught, a constant. So then we can do calculus, right? We have what? We have d omega dt is equal to alpha naught, right? What's that tell me about omega? That tells me integrating that omega is equal to omega naught plus alpha naught times t. Now you can say, it seems like you chose your integration constant somewhat conveniently. That's true. My integration constant was omega naught. I argue that that's good notation because if you put in times 0, what do you get?
Omega naught.
Omega naught. So I'm saying omega naught is the angular velocity at time 0. So, but I just integrate and I get that. And then of course, we have what? We have d theta dt, right, is equal to omega but omega is omega naught plus alpha naught t. So if I integrate that, again, just keeping it short here, I'll just, for my own purposes, add theta naught right here because I know it's going to, well, you can take it or leave it. We could drag the calculus out here and I could talk about it for 10 minutes, but people who understood before would still understand. The people who didn't understand before would still understand, so forth. I mean, I'm happy to teach you calculus 1 if you have questions about it, but I'm not going to try to do it to you here. So you can see if you put in time 0, that term drops, and you're just left with theta equals to theta naught. So theta naught, you should understand, is the angle at time 0. Right? Omega naught is the angular velocity at time 0. Do you recognize? I mean, these, you're like, but didn't we do this before? Yeah, we kind of did. Let's see, what was the other thing we did? Okay, so another thing we can do is that d omega dt is equal to alpha naught implies what? That implies that the theta dt, d omega d theta, is equal to alpha naught, which we can re-look at as omega, d omega is equal to alpha naught d theta. Separate variables, integrate both sides, integrate over the appropriate things. I integrate the left-hand side from omega naught to omega. I'll put an F there just to feel less guilty about the math here. And theta naught, let's say theta f. And when I do those integrals, what am I left with? I'm left with 1/2 omega f squared minus omega naught squared is equal to alpha naught theta f minus theta naught. Of course, this is the timeless equation, right? Let me clean it up. What we have is that omega f squared is equal to omega naught squared plus 2 alpha naught, the change in theta. So we're starting to build a dictionary, right? I mean, a bridge between worlds, if you like. There's 2 worlds. Over here we have linear. Over here we have rotational. So in linear, we had position, x. In the rotational world, by analogy, we have theta. The position and angle, the position in radians, right? Then we had speed, or velocity v, which of course was dx dt, right? Over here, we've got omega. In the position world, we had acceleration, right? In the rotational world, we have angular acceleration. And these are defined in analogy with respect to each other, right? So let's see here. There was another thing we derived in the linear case, right? One of the things I derived in the linear case was that the average velocity was the average velocity, right? So what do I mean by that? I mean the average was also equal to like v1 plus v2 divided by 2, you know, where that's also equal to the change in x over the change in t. To be more specific, x2 minus x1 over t2 minus t1, right? There's a specific subclass of particularly draconian homework problems that require use of this average velocity relation. These are like 8th level monsters, if the rest of the homework is 4th level. I don't know. If you need this in a homework problem, that's an easy problem. But they exist. So if you know this average velocity is the average of the velocities relation, you already know what happens by the dictionary. You know what is the corresponding angular thing. It's that the average angular velocity, right? It's also equal to the change in theta over the change in t, but you know what else it is? It's omega 1 plus omega 2 divided by 2. Because the mathematics we did earlier goes through, line by line, by this analogy. Okay. So these are your fundamental building blocks for solving kinematic problems about rotations. Let's work an example. Do we have enough to work an example now? Let's do it. Yeah, it is a lot of equations, that is true, but I hope that these are kind of like you know. So it's kind of a standard problem. You got some like grinding wheel or something, right? And it could be that. And suppose it's got, you know, the initial angular speed is something like 1,000 radians per second. All right. And then suppose a brake stops, stops the wheel in, 1 minute. All right. You can also give us the radius. Let's suppose that the radius is 0.5 meters, okay? So I can ask the questions, right? Like, what is the total angle through which the wheel turns during this process?
That's change in data.
Right, what's the change in data? And I could ask, what's the total number of revolutions of the wheel? I could also ask, how much arc length would a point on the wheel trace out? You know, those three questions are very much related. So how would you solve this problem? I could do other things too, right? I could ask, like, what's the centripetal acceleration at the start of a point on the wheel, on the rim of the wheel? How would you do that? You just use what I just erased, right? The radius times omega squared. Whoa. 0.5 times a million. Holy cow. That's, wow. Ouch. Okay.
But that would be constantly changing, right? Is the brake?
Yeah. Excuse me. Okay, so how do we solve this? We can find the angular acceleration. How?
Omega final is equal to omega naught plus alpha t.
Yeah, right. Basically solve this equation for alpha. So you say take omega final minus omega initial divided by the change in t, and that'll work. So the final omega, of course, is 0, right? The initial omega is 1,000, so I've got minus 1,000 radians per second. And how much is a minute? 60 seconds. So what's that work out to? Oh man, I just don't have anything today. You guys got a number for me?
16.67.
So minus 16.67 what?
Radians per second.
Yeah, radians per second, or per second squared is what I usually say. So, okay, well, you didn't ask for that. Well, I know, but it's helpful to find what we're looking for, right? So, then what? Well, I can use this, of course, or I could use that, I suppose. I don't know. I'm kind of ambivalent. I could go this way or that way. I'll go with the timeless equation. So timeless equation, I have omega f squared equals omega naught squared plus 2 alpha change in theta. I usually drop the sub naughts once I'm in a specific problem. The reason I put a sub naught on the alpha in this derivation was just to separate it conceptually from the abstract notion of angular acceleration, from the fact that a specific given constant was, what was describing the problem. So anyway. That's why I'm saying there's no knot here. It's just alpha's a constant, So why put a knot there? Get away with not doing it. Oh, I'm sorry. Okay, so change in theta apparently is minus omega naught squared divided by 2 alpha, because omega f of course is 0, right? Because we're saying it breaks the stop, and so we've got minus 16.67 squared divided by, I'm an idiot. What was omega naught? So minus 1,000 squared divided by 2 times minus 16.67. Of course, the minus will cancel because the change in theta is positive, right? So what's 1,000,000 divided by 32? 33 reference speaking. Can you get
Yeah, 30,000.
29,994.
30,000. I guess I used the more exact version
It would
of
round.
acceleration. 30 what? 30,000.
30,000. Okay, radians. So how many revolutions? What's that?
4,774.
1,734. All right, let me take a breath here. Everybody understand what we're doing? So when you attack the problem with rotations, it's basically the same logic that we used before for the kinematics problem at the start of the course, right? You want to identify your acceleration, your angular acceleration. You want to identify, do you have an initial velocity? Excuse me, initial angular velocity? Do you have an initial, a final angular velocity? What are you given? Do you know theta f? Do you know theta naught? The other game that can be played here, though, that's kind of new, is they can give you things in terms of the tangential velocity or the tangential acceleration, right? And sometimes, like, if they tell you the tangential, like, instead of saying 1,000 radians per second, I could have started this problem by saying a point on the rim has a speed of, 500 meters per second. And I could have started the problem that way. See, because telling you the tangential speed is 500 meters per second, and I could be wrong, let's see here, v is supposed to be, I'm trying to figure out, v is omega naught r, right? So that's, trying to make sure I'm consistent here, 1,000 radians per second. My radius is 0.5 meters. Okay, so yeah, 500 meters per second would be the initial speed there. Just, yeah, it's kind of moving. Do you guys know how fast CDs, like or a DVD spins?
I don't remember, but I know that max is 1,000 revolutions per second.
Yeah.
20,000
Before
That's
it
their
breaks.
max before they warp and break.
20,000 RPM? Revolutions per minute, probably?
That's before they warp and break. Yeah.
That's a good question. So revolutions per minute, how would you change that into, what would the angular velocity be? If I tell you 20,000 revolutions per minute, what's the angular velocity? That'd be a little problem to work. Let's do it. Let's see here, so omega equal to 20,000 RPM. Well, first of all, let's put that in a more, first of all, commas. Who needs commas? So fifth grade. Revolutions per minute. Well, that's revolutions over minute. I think RPM is a useless notation. It has no mathematical content. Okay. Let's see here. So this is 2 pi radians in 1 revolution. Right, that will cancel my revolutions and replace me with radians. And minutes, well, we all know that a minute is 60 seconds. So if I multiply by those factors, then I will be good to go. Except that I can't run a calculator, so pretty much just waiting for you guys to give me a number.
2,094 radians per second.
Agreed? Now, if that's a CD or a DVD, right? That's probably a little bit too big. It's too big, it's good.
Just gonna try
I don't know, I can't, it's either too big or too little, I mean, roughly speaking like this, right? So what's the radius approximately? I mean, it's something like this, right? No. We got a CD on them?
Those dates are long.
Yeah, really. So let's go.
Who's got the computers?
So like 5 years ago or whatever. Oh, wait, that's
You could measure the disk drive on computers.
Actually, I think it
Oh, it's a very useful.
Back to the book.
What is
Okay, what's going? Yay for worthless.
Stop taking it.
I will, now I'm going to measure rim to rim. I got 12 centimeters diameter. If the diameter is 12 centimeters, what's the radius?
About 6.
So approximately 6 centimeters, right? Which is 0.06 meters. So what's what's the linear velocity? It's approximately 0.06 meters times 2,094 radians per second. This is like just before it breaks speed. I trust you guys. I think I do. Seems like the sort of thing you know. What do we got? What?
Meters per second.
What is it?
125.
125.7 meters per second. Do you guys remember the conversion to miles per hour? I think it means more if we can put in miles per hour. You guys?
2.5.
So how about 3,600 is the number of seconds in an hour, and 1,609 is the number of meters in a mile.
It's no, that's not right.
That's ridiculous. So basically, if you turn one into a launcher,
Yeah.
What we got? 281 miles per hour.
oh wow.
To think it's like how far
They don't spin that fast.
Yeah, that's the highest they can get before it breaks.
Right. So I mean, it's
Well, what happened if it did break? If
It would
goes
shatter.
flying.
It shattered.
There are videos of
I
it.
just saw it. They filmed it under 70,000 frames per second.
you notice that the it's like, if you think about it, v is equal to r omega, right? So if you half the angular speed, you half the linear speed, right? So if it's only at like 1,000 RPM, 1,000 radians per second rather, or 10,000 RPM, then you only got a speed of, 140. And I seem to recall more like 2,000 RPM or 3,000 RPM is typical speed.
Some people consider it a typical hard drive speed.
Yeah. I think hard drives are a little bit smaller, right? 3.5 inches, so we're talking 0. That is probably, something like that is, so I think maybe a limiting device characteristic is basically a couple hundred miles an hour, about the fastest you want stuff spinning inside something that you sit on your lap. I think this is an argument for solid state drives, yes?
Yes.
Why doesn't everything come with a solid state drive now, by the way?
Mine is high.
Yeah, it's
Really
super
expensive.
expensive.
They're not really expensive.
But if it boots your computer like 5 times as fast, why does it never really sell tasty solid state drives?
Mine has
I
a
don't
hybrid.
understand.
Well, they're starting to do like hybrids now where they have like hard drive where you start everything on it and then solid state for like the
But
start.
according to,
Yeah, hybrids are
according to
stupid.
my authority, that's just a gimmick and they're not really that good.
Yeah,
They work
it's-
there.
Not the best.
In my authority is somewhat some education. He's like 2 PhDs worth, but anyway, you know what I'm talking about. A certain mind. But okay, go ahead. Yes, Dr. Wayne was very happy when he learned that I bought my wife a gaming laptop. So she now grades her blackboards for the online math course using an Asus ROG. Yes. No, it's last year's model. It's not the most current thing, but
Still doesn't matter. Nothing's better than mine, so.
all right.
I don't care about that.
I need to watch it. What time is it?
2. 223.
223? Ah, you told me that. Okay, so of course you can work more problems like this, right? But also of interest is the topic of rotational kinetic energy, right? So how about kinetic energy in rotational case? I'm probably jumping the gun here. I'm almost certainly jumping the gun. I should probably not talk about that yet. I'd probably talk about what goes first.
Shouldn't be that hard.
Well, the thing is,
Expert.
Expert gonna go first. Okay, I guess I have to. Guess I have to respect today.
You already win.
So, next thing to really talk about is the moment of inertia. You know, what is the moment of inertia? So for a single mass, all right, there's a distance, say, r from the, the pivot point, let's say. So talking about moment of inertia, we're talking about rotational motion with respect to some coordinate system. So there's some origin with which we're measuring things, and if we change the origin, it changes the physics. So there's always like an implicit choice of coordinates in what I'm talking about. So suppose that the origin is there, r is the distance from the origin to the mass. The moment of inertia for a simple mass is simply this. I, we use I for moment of inertia, is equal to m r squared. Right? So, let's see here, how can I say this? Now you say, well, who cares? I mean, what's the point of moment of inertia? Well, that is a good question.
So it's length squared times mass.
Yeah, it's kilogram meters squared is the units. And I don't think I have enough time to do it justice, Dave. I'm just going to kind of tell you the big picture, and then I haven't really motivated why this is a reasonable formula yet, and it's going to take me about a half an hour another day to do it. Okay, so I mean, that's just I'll come clean on that. Let me just share this with you. It turns out that the kinetic energy, all right, is equal to 1/2, and this is the rotational kinetic energy, okay? Rotational kinetic energy. Turns out it ends up being 1/2 I omega squared. So the moment of inertia plays the role that mass did before for rotational motion. So we will soon learn how to work problems. I'm just kind of giving you a brief view ahead. Here's a problem we'll be able to work after a class or two. You have a bowling ball rolling along a plane, and you can ask what's its total energy, rolling without slipping, all right? So if the bowling ball is rolling without slipping, it's got some velocity this way, and as it's rolling, right? So that connects the velocity, the linear velocity, to the rotational velocity. Omega is actually equal to RV. So if you think about it, right? Contrast two situations. You have a bowling ball rolling without slipping, right? Whereas you just have a bowling ball gliding along. If the velocity is the same, the one that's spinning has more energy, because it also has this rotational energy, right? So the total energy then is a sum of two kinds of energies in this mechanical case. There's the linear translational kinetic energy, which we've already talked about earlier in this course, and now this newfangled thing, this rotational kinetic energy. And the way it works is pretty simple. The total kinetic energy for such a rolling bowling ball would be 1/2 times the mass of the bowling ball times the velocity squared, plus 1/2 I times omega squared. But this would be the moment of inertia for a bowling ball. So the moment of inertia for a point particle is just mr squared. It turns out for a sphere of radius r, the moment of inertia works out to, if I recall correctly, 2/5 mr squared. Say, well, how do you know the moment of inertia for a sphere is 2/5 mr squared? Calculus. So But anyway, that if you look at it though, that there's two parts of the kinetic energy. There's the translational and there's the rotational. So that's one of the kind of problem we're going to be able to solve with this once we're a little bit further. Okay. So anyway, I owe you a more systematic discussion of moment of inertia, and also just how do we talk about when you have a system of particles like rotating. You know, what can you say about physics there, the dynamics? In other words, we're talking about what's called angular momentum to describe rotation of a system, like we talked about momentum to describe conservation of linear momentum. Yeah.
Does the kinetic energy change for a sphere?
Kinetic energy change?
For a sphere, does that change on?
Yeah, again, if it everything else being equal, if it has the same speed and it's rolling, there's more energy because it also has the rolling energy, the spinning energy. To contrast it, the bowling ball could be spinning just in one place, just like that, and it has all that rotational energy, even though it's not moving anywhere. So, you know, before this point in the course, if it was spinning, we would have been like, you'd ask how much kinetic energy does it have? You'd be like, I don't, it's not moving, so kinetic energy is zero, right? Well, it's moving in a circular way, right? So that's a new kind of motion that we're just now describing.
So like a top.
Yeah, top would have rotational kinetic energy. Yes, sir.
This may be a slightly silly question. Can we still work with concepts like work equals the change in kinetic energy and rotational motion?
It turns out what we're going to derive is that for a system of particles, if the net torque on the system is zero, then angular momentum is conserved. And so the angular momentum will change if there's non-zero torque on the system. Torque being a measure, well, torque is going to play the role that force did before. All right, so torque is going to be like force. Torque is going to have the ability to create a non-zero angular acceleration, and so thereby change the angular velocity and thereby change the net rotational kinetic energy for the system. Anyway, obviously I can't do all those things in 10 minutes, so let's just start. Yeah. Thanks, guys.